Okay, so we're very happy to have Bartosz Wcisło giving the second part of this talk, Model Theoretic Characterizations of Truth. My apologies on my attempt at pronouncing Polish. But Bartek comes to us from Gdansk. Again, my apologies. And this is, I believe, your third time speaking at MOPA, or fourth?
Yes.
But it's very nice to have you sort of as a repeat speaker here. So so take it away. I'm very excited for this.
Okay, let's see. Hello, hi to all of you. It's very nice and always a very great pleasure to speak at your seminar here at MOPA. And by the way, you're really doing very well as far as pronunciation of Polish proper names goes. So I'm really impressed, actually. Okay, so going to the topic. So this talk is again, like it's part 2. So of course the topic didn't change that much. So it's again about the interaction between the presence of a truth predicate in a model on one hand side, and then the purely model theoretic properties of them. What are those? I mean, Mateusz sketched some of these. So we know that the presence of a truth predicate imposes some pure model theoretic conditions on models of arithmetic. So now the general broad question is this. So suppose we have a theory U that also imposes those same model theoretic conditions. We'll see examples. You saw some examples in Mateusz's talk. Does it mean that theory U does this mean that the theory U defines a truth predicate, right? So define here can mean various things. Truth predicate can mean actually various things depending on what exact axioms you demand. But the general goal is to try to revert. We know that sometimes truth properties impose model theoretic conditions. So it's a kind of reverse to this question. Assume you can impose those model theoretic conditions. Can you extract some truth predicate from a theory, assuming that it does? So as you can guess, of course, it's a joint work with Mateusz, probably very unsurprisingly. So once more, the general question. Like I'm essentially repeating the previous slide because well, this is the driving motivation for the whole talk. So suppose we have a theory U, it extends, and to make it more precise, suppose we have a theory U, it extends some portion of PA, some fragment of PA. It imposes some truth-related properties, so theories, properties that usually come with a truth predicate. So then, does that theory U define a truth predicate? And what can it mean? Actually, it can mean various things depending on how you make parts of the statement precise. So there can be, you first fix what's exact fragment you're investigating. Then you have to tell me what is the truth-like property you consider. What do you actually mean by a truth predicate? So this can also mean many different things depending on what's your axioms, what's your truth theoretic axioms. What do you mean by define, right? Mateusz recently introduced this piece of notation, model theoretically defines. So in every model, it defines passively with parameters. We can, of course, mean other things like the usual definability relation, that one theory simply defines a predicate satisfying the other theory. So kind of very restrictive interpretability condition. We can also mean whenever in one model you have a predicate satisfying one theory, so whenever a model expands to a theory, right? This is another notion, so let me draw it. So whenever you have a model M which expands to a theory U, does that mean that it also expands to a theory in possibly different way, that it expands to some truth theory T, right? So this is kind of general questions we're we try to investigate. And of course, if you vary many things along the way, you get many different questions. Right. So this part, so the previous talk was the property, the truth-like property considered in the last talk by Mateusz was imposing elementarity between models. So Mateusz was mostly interested in the property. Suppose you have two models of some theory. Suppose that having two models of the theory such that one model M is a submodel of some model M prime, and they both satisfy U. So does that imply, so this implies that restricted to languages of PA, M becomes elementary M prime, right? So this was imposing an elementarity considered by Mateusz. And it turned out that if a theory U has this property, then like with some, like with some extra assumptions, but not so many, it actually does define some very nice truth predicate. So here now we'll talk about recursive saturation or computable saturation of models. So we will be interested in the question, suppose that you have a fragment of PA, or well, essentially for us, a fragment of PA, and you assume that you have a theory such that every arithmetical part of its model, so that the arithmetical part of its model is recursively saturated. So it imposes recursive saturation of the arithmetical part. Does that mean that it satisfies some truth, that it defines some truth predicate? And in what way does it define it? And of course, there's a number of other interesting properties. So Albert last time, for example, proposed a property like it compactifies PA, it defines PA in a finite way. So it was actually also one of the properties we considered in this research, but this particular unsuccessfully. Okay, so let's now introduce the interesting truth predicate. I mean, the truth predicates with which we'll be concerned in this particular talk. You've already seen this, if not for, definitely, for instance, in Mateusz's talk, but of course that you've probably seen it also before, for example, in the talks Mateusz or I have given the seminars. U to be minus uniform authority by conditionals, let me just remind you, is a theory that extends P with a fresh predicate T, with the interpretation that X is a Gödel code of a true arithmetical sentence in the following axiom scheme. So if we forget about this biggish parenthesis, things in parentheses, then it really is just Tarski scheme, right? Phi is true if and only if phi. But then you want to make it uniform, which means that you allow to insert arbitrary codes of terms. So this is really a quantifier. This is not a scheme. So you allow substitution of arbitrary arithmetical closed terms, formal substitution. They say that the result is true if and only if the value, like phi holds of the values of the terms. So it's something you can say in a quantified manner. Like, of course, you would need much more decoration here. So for each T1, Tn, if there are codes of closed arithmetical terms, then the effect of the substitution of those terms to phi is true if and only if for every Z1 up to Zn, such that there are formally computed values of those terms, phi holds of Z1, Zn. So there's not more decoration to it, but it really says this. And this is a scheme over formula. So you quantify over terms, you treat formula schematically. You can add full induction scheme. This resulting theory is called UTB without minus, and this is a theory of inductive satisfaction class, so a very classical object of models of arithmetic. Okay. Right. So now there is a different characterization of UTB, slightly different, that will be of much interest to us. So namely, observe that having uniform statistic by conditionals in non-standard models really means that you have a non-standard predicate which is compositional for formulae up to some non-standard syntactic depth. So it's compositional for formulae which are standard by UTB. So uniform Tarski by conditionals impose, of course, compositionality on a standardly deep formulae, and then you can spill over this property and see that actually there exists a non-standard C. So this is actually non-standard. Such that S satisfies compositional conditions for formulae of syntactic depth less or equals C. So the following holds if you see an equality of terms. It's true if and only if those terms have actually equal values. A negated sentence which is not too big is true if and only if a negation is true if it's not too big and the negated sentence is false. Not too big disjunctions are true if and only if one of the disjunctions is not too big. Existential formulae are true if and only if they are witnessed by some numeral. And to make this smoother, we assume that we can resubstitute freely sequences of terms with the same values. This will not play any major role in this particular talk. So this theory can be, you have a natural notation for it. It's compositional truth, which you've already seen, restricted up to some initial segment. Well, of course, you can. This also makes sense without induction. We can call it CT minus restricted to C. It also makes sense if you restrict compositional axioms to a cut, which will make it denoted CT minus restricted to some I. It also makes sense not to restrict those axioms at all. It will be CT minus. Of course, this direct link between UTB and compositional axioms holds in this particular formulation or only for UTB, right? So if you have UTB, then you have CT up to C. If you have UTB minus, then you have CT minus restricted up to some initial segment, which can be actually a cut. It can have the greatest element, or actually it could be the whole model. It can also be a standard cut. So options are wider. Okay, that's.
So can I ask?
Yes, of course. Mm-hmm.
Just trying to parse what you write here. You say that there exists a T such that S satisfies Tarski's compositional conditions. I mean. Yes. I guess what I originally wanted to ask before I just parse this is it just true that just S satisfies these conditions, right? That if S is a model of PA star and and you have UTB, then maybe S, but we don't even have to say anything else about getting another truth predicate T, right? S itself.
Yes and no. So
yes and no. Okay. Right.
Yes, so it's okay. So it's true that S, because the situation is a model of PA, and S satisfies UTB, then actually, of course, S, there will be actual C such that S restricted to depth C. This very particular restriction will satisfy CT up to C, but actually, of course, this S can also be extended further and up above this fixed level, and can be completely nonsense, right? But you're right that actually it's S. So it's half a typo, but it's a typo, but actually not. The typo shouldn't be that confusing.
Mm-hmm. in the sense that everything above it might be nonsense, but in terms of like just satisfying CT restricted to C, the axioms don't say anything about the stuff that's too high, right? So S on its own doesn't, right? S on its own should satisfy CT up to some non-standard element. Is that right? Okay.
Why does predicate have models? Let me remind you of a very simple argument. So how do we get recursive saturation? Suppose you have a model of UTB with a non-standard arithmetical part, then M is recursively saturated. So that's the first, the most basic link you can have. So you have a model of UTB. So uniform Tarski by conditionals plus induction, M is non-standard. So M has a satisfaction plus a more classical language. Then M, the arithmetical part, is recursively saturated. This is like very simple argument, fix a recursive type. So it's phi0, phi1, blah, blah, blah. This is a type in this model. This model satisfies UTB. So it's finitely satisfied in the model. And for every n you have, there exists x, such that all formulae below n are true of this type phi, are true of this x. You can write it down since this type, this sequence is definable, since it's recursive. So if you spill over n, you get a non-standard C such that there is an element such that phi of I is true of every, such that every formula below C from that type is true of that element. Right? So since you have UTB and this is quantification, you see that this one witness X satisfies phi0, it satisfies phi1, and so on. So it actually does realize your type. As you can see, the proposition is very simple. And the first reversal to it, so the first reversal of the kind we are trying to investigate comes from Roman. I mean, the first reversal that I know of. So take a theory in a countable language, extending PA, that contains the full induction scheme for the extended language. Suppose that for any non-standard model of that theory, its arithmetical reduct is recursively saturated. So we're exactly in the situation as with UTB. Then in every model M of U, we can define with parameters a predicate T, which satisfies UTB. Yeah, the process maybe not very fortunate, right? So for UTB, you get as good a reversal as you could imagine. So as long as you have a theory that extends PA, it contains the full induction scheme and imposes recursive saturation, then it model defines UTB. Model defines in the balance that Mateusz introduced last time. So UTB is the like the exact reason why theories can impose recursive saturation. The argument is extremely elegant. I really enjoyed it, and in fact, it's very kind of very neat and very smooth. So recall theorem from Dallas-Becker. So suppose you have mostly recall what the assumptions were. So suppose you have a theory in a countable language with the full induction scheme, then you can end extend conservatively. So what does it mean that the extension is conservative? This means that if you define a set A in the end extension, then its intersection with the original model is actually definable in that model. I'm sorry, I know that all of you here know this stuff perfectly well, but I know it will be recorded. Like I have this slight dim hope that maybe someone will listen to the recording. And from this moment on, we'll probably start discussing new things. Let's finish the argument of Romankosak theorem. So take this theory U, satisfying the assumption of the theorem. So it's countable language, induction plus it imposes recursive saturation. It satisfies the assumption of Magdalena-Specker. So you can end extend it conservatively and elementarily in the sense of the theory U, right? So with the whole bunch of those extra predicates. Consider the following type. This I'm writing down this type explicitly because it will play a prominent role in the next part of the talk, like in the next half of the talk. So what does it say? It says Y codes the portion of elementary diagram of M with for elements for parameters up to X. So this is like slightly more subtle. So we have to say that since we try to work in this setting of truth theory, so you actually say here that those are not elements less than X, but terms less than X. And of course you have to play with those values, but essentially it says this, that Y is the coded portion of elementary diagram with parameters up to X. Well, the arithmetical elementary diagram, of course. So now pick any C, great M non-standard C. Since N satisfies U, it realizes this type tau with parameter C. Right? This is an arithmetical type. This model N is recursively saturated. It satisfies U, so it's recursively saturated, so it does realize the type T tau. Take any element realizing this type. If you just look at this element as a set, so the elementary diagram with all the parameters up to some C, where C is not in M, is greater than M. Then of course what you get is satisfies U to B. By conservativity, it's definable. In particular, it satisfies induction. So this will be not only U to B minus, but also the whole U to B. Very neat, very beautiful argument. Just once more, let me draw it. So we start with a model. M. You end extend it to a model N. This is a conservative end extension. Here you have elementary diagram up to C. So here you pick some C. Here is elementary diagram up to C. This is D. You look at what this decodes. This part is T. It thus satisfies U to B minus, since it's a part of elementary diagram. On the other hand, it's conservative. So it's definable in M. So M defines this truth predicate. Very non-constructive. You don't see how this is defined, but here it is. And very beautiful on the other hand, and very simple. Very nice, very neat. Okay, less obvious example. Suppose that you have a model, it satisfies CT minus. Suppose that you have a model of, less obvious example of what? Of imposing recursive saturation. So this is Latham's theorem. If you get CT minus, so compositional truth, but without induction, then the underlying model is recursively saturated. So this induction scheme was not entirely crucial, but it's not obvious that CT minus is a counterexample. So we know it's not a counterexample of the Latham's theorem, actually. It doesn't satisfy induction, but in fact, it does define UTB. So it's not obvious whether maybe this recursive saturation would have to factor for UTB after all. This is imposing recursive saturation. Okay, so the rest of the talk will be like a part of our research, which is about reversing those model theoretic results about truth. So extracting the truth from imposing model theoretic conditions. So now we'll try to see what are the possible improvements and present some results and non-results concerning improving the result of Kosak. So first question, can you literally drop some assumptions? or literally strengthen the conclusion in some way. So one thing we cannot do is that we cannot literally drop the assumptions about the induction of theory. So the previous example could suggest that maybe you come up with something general enough so that also would cover CT minus, let's say. So if you have a theory which does impose recursive saturation, so do you automatically have to have UTB, right? Maybe that would be the truth. This is not this is not true. So here's the proposition. So you can have a theory U that has that's in countable language. It extends PA. I don't write anything about induction, but it does impose recursive saturation. So everything as in Kosak's theorem except for induction for U, for the extended language of U. So there is such a theory that has a model N that cannot be expanded to a model of UTB. So like first naive attempt won't work. Of what can you do? How can you push the boundaries of Kosak's result? Why? Again, it's something I guess you all know perfectly well. Let's see, there was following theorem of Kaufman and Scheller. So you can have, there are recursively saturated models of PA which are rather classless, which means that for any X, for any class, if that is a class, if it's piecewise coded, so every bounded part is arithmetically coded in the model, then it's definable. So there are no other classes. You can show that necessarily such a model has to be uncountable, because of course countable models are countable recursively saturated models of PA are resplendent. Yeah, here I just say what piecewise coded means. We mean that for every C, you can code X intersected with C as a finite set in the sense of PA. And how can you get your theory imposing recursive saturation which doesn't define UTB? Well, you can just characterize a theory that essentially says the model is recursively saturated. So consider the following theory, URS, uniform recursive saturation. It imposes PA with the following axioms. If for any recursive type P for any N, it says if P is satisfied finitely up to N. So if there is something that jointly satisfies the first N sentences of P, of the type P, then CP, this is a fresh new function symbol. This shouldn't be double. This should be just CPU. I mean this should be, the parentheses are not right. So what I really mean is this, right? So you have a function CP. So CP is this witness for P. It's as good as you can get, right? If you have N, if you have something satisfies first and formulae of P, then CP does satisfy it, and then you make it kind of uniform with those extra parameters. Why? Because it can depend on parameters, hence uniformity. So you can check that a mod contrary to our previous conventions, here I don't add induction, so maybe to make it more consistent I should have named it URS minus. So then you can like directly on your fingers verify that the model expands to URS only if it's recursively saturated. So in particular, if M is a rather classless recursively saturated model of PA, then it expands to URS but not to UTB. So you cannot strengthen directly Kosak's theorem in that manner. Right. Let's continue. So how about strengthening the kind of definability? So in Kosak's result, you know that in every model you can define a predicate satisfying UTB. So Ali Enayat, when I first gave this talk on our seminar in Warsaw, asked me whether dependence, whether you can make Kosak's result more explicit. So can give the explicit uniform dependence on what this definition will be depending on what the theory U was. So this result in a way shows that this is impossible. So the dependence can be non-uniform. It can be, the definition can be simply different from a model to a model. So here's the proposition. You can have a theory U in a countable language with full induction, such that every model of U, the arithmetical reduct of n is recursively saturated. So it all mimics. So those are the exact assumptions of Kosak's result. But this theory U does not define a predicate probably satisfying Q to B. Right, so we know by Kosak's result that it does define it model by model. In every model, it does define it with parameters, but you cannot have a uniform definition that works in theory. It doesn't interpret it one-dimensionally, like not changing domain and so on, and not changing arithmetical symbols. Right, so what's the counterexample that will fit in this one slide? Fix some background enumeration of arithmetical formulae and to take the following theory. You have infinitely many truth predicates, T0, T1, blah, 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 up to and including T omega. You have full induction for this language. And for each I and j, you have the following axiom. So what does it say? If Tj fails to satisfy UTB minus, so here j and I are possibly different. So if j it doesn't do the full job of being a UTB minus predicate, then T omega has to take over parts of its duties. Namely, it takes Vj. Right? It's as I said in the first seminar, it's like administrative duties. So there are many guys. If some of them completely doesn't do their job, then you have to take part of slight portion of their responsibilities and duties. Okay. So if you have a model of U, then there is a predicate satisfying QDB, namely, well, either all of Ti for natural I satisfy UTB, so either some Ti satisfies UTB, then we're done, or no Ti satisfies UTB, then T omega satisfies UTB for all the Vj, right? So either one of those Tj's satisfies UTB and you're happy, or it doesn't, and then this means that T omega has to take part by part the whole job. On the other hand, there is no definition, no uniform definition. So suppose there is a predicate, suppose that you have a predicate satisfying QTB definable in U. We'll get a contradiction. So if it's definable with one particular formula. This formula only uses predicates T0 up to Tn and T on possibly T omega. So it only uses finitely many of those predicates. And then you can do the simplest counterexample. So you take a model of U such that those predicates that you actually did mention in phi are simply empty. They're empty sets, right? All the predicates above this n, so all the predicates you don't mention are satisfy UTB. They are actually the standard arithmetical truth set. T omega is some partial arithmetical truth predicate which works fine for phi0 up to phi n. And I didn't say this, but point 0 should be arithmetical, or the arithmetical part is simply standard, right? So it's an expansion of the standard model. So in the standard model, you fix all predicates you did mention as empty. You fix the predicate T omega as some partial truth predicate that takes over the job of T0 up to Tn. So it works for phi0 up to phi(n). And all the other truth predicates are standard full truth predicates. Well, all of those predicates are in this model arithmetically definable. So phi in particular defines an arithmetical set. So whatever it defines cannot be a truth predicate in arithmetical mode. So definability of UTP by Kosak's result is never fully uniform. So it has to depend on particularities of the model in a very brutal way.
But Bartosz, does this argument crucially depend on the infinite signature?
No, that's a very good question. Of course, that's the first question we ask ourselves. It doesn't. So we have a counterexample that works for a finite language, but good. It's way more complicated. It's way more. I mean, it's very similar. So this is really the same example. So you have like to massage it a little bit, but it's the same example. But you have to replace this part that you've mentioned only finitely many predicates. So phi defines an arithmetical set. So you replace this consideration of how many predicates you used with the consideration of how complex the formula is. Mm-hmm. So you, in your theory, you say you have to use some computability theory, and you say that you have a predicate that encodes a UTP predicate either in a very simple manner. If it doesn't do it in a very simple manner, then some other. So you have one predicate T omega as before. So if your set doesn't decode to a truth predicate in a very simple manner with Oracle zero jump, then then T omega defines a truth predicate. It works fine for phi0. If it doesn't decode to a truth predicate with a formula which is sigma 2, then your predicate T omega works fine for phi2, and so forth and so on. So it's very similar structure of the argument, but then you have to like take care that this coding can be really done, that we use some kind of generic sets and this kind of, I mean, it becomes much more computability theoretic flavored. What we don't know is whether you can do this, whether it depends on the finiteness of the theory. So whether it holds, whether we can have a counterexample for a finite theory is still on our list of to do.
I see, yes.
So it doesn't depend on signature, but for now it does depend on finiteness of theory.
Good, thank you.
Very good question. Thank you. Thank you for asking this question. Okay, so can you? Finally, we can say something positive. So one thing we can do, you can drop induction altogether all along the way. So both in conclusion and in in the assumptions. So suppose that you, as a theory in countable language, as in Kosak's theory, it extends PA, assume that every reduct is recursively saturated. So we're still in the situation when you impose recursive saturation, but no induction. I don't assume any induction. Then in every model of U, you can define with parameters. So it's model theoretic definability in Mateusz's parlance. A set T such that it satisfies UTP minus. So if you drop induction in Kosak's result in the assumptions and you drop it in the conclusions, that this result actually does hold. So once again, you give me a theory, countable language, extends PA. Actually, here it's enough that it's a fragment. It works fine over S12, or I guess it works fine over S12. I didn't check it, but it definitely works fine over elementary arithmetic. It imposes recursive saturation, then it defines uniform Tarski by conditionals with no induction, possible with no induction. How do you prove it? So first, maybe to understand what will be going on in the next slide, our first naive wrong attempt.
May I have a question?
Yes, right.
Sorry, regarding.
Sure.
So isn't that we can drop this parenthetical remark that the definability is with parameters? Because if you know that
yes, we can actually in the proof we can. I mean, I want yes.
So it's definability without parameters.
Yes. I mean, I wanted to stick to one notion, so like possible with parameters, but in this case, it actually will be just non-uniform. So it depends on the model, but not necessarily on the parameters. Right? You're right. You're right. Just simply because we used in the previous talk this model definability. You can define every model possibly with parameters. So I wanted to stick just to this notion. But here it's non-uniform.
Yeah, but I asked this question precisely because in the previous talk I said that we can do without parameters. So that's,
okay, I'm sorry then for
I wanted to press on that.
Okay. So first, let's start with a non-proof, with a mistaken proof. You extend your theory with a fresh constant C. Every model of U is recursively saturated. So the type tau, which I introduced before. So this says Y codes a portion of elementary diagram with parameters up to C. So it's realized in every model. That so far so good. Okay. So now I say that there has to be a formula Psi, which actually defines this element satisfying type tau. So actually there has to be a formula that does satisfy this type, this portion of a truth predicate depending on C. Because otherwise I would run an omitting type theorem and find a model in which type tau is not definable, and then this would contradict the properties of U that it's assumed to impose recursive saturation. If you have those type tau, if you have those elements satisfying type tau, we can glue them together. So you have, I mean, all I'm saying will be a wrong proof, right? So you have a you have a portion, you have some portion that C0, and here is something that satisfies. So here is one, your D1, right? D0. It satisfies this portion of the type. Then you have some C1. Here is D1, which satisfies, which codes elementary diagram up to C1. And you can define it so forth and so on. It seems you can glue it because all those D's are defined with the very same formula Psi. So you simply say there are cofinally many Y's satisfying Psi of XY. So this formula defining portions of elementary diagram, which satisfies some coherence conditions. So those sets can in a sense be coherent with each other. It will come up in the actual proof in the next couple of minutes. So I'm not spelling it out now, but you can imagine, like kind of they don't contradict each other too brutally. And phi is in one of those sets. Seems like an argument. Okay, it's almost good, and it actually what actually is the inspiration for the actual proof. But the problem is that, as stated in any of our favorite textbooks, omitting types works only for complete theories, right? So this formula of C, it actually depends on the type of C, right? If you add a constant, then to complete a theory, if you add a constant, then to complete a theory, in particular, requires you to find the type of that constant. And so if C depends on C, if it's really indexed by the element, then there's possibly nothing to glue together. It might be that those elements are definable by different formulae, but actually saying that they are definable, each of those portions of elementary diagram is definable with a different formula is trivial. Of course, they are definable with some formula using infinitely many different parameters, right? I mean, just take any such portion of elementary diagram and say I'm one of the I am this portion, and then say I'm this portion, I'm this portion. So of course, if you if you allow trivial dependence, then there's nothing interesting in it. But we can try to make it better. So actually we fixed that attempt. The idea comes from a paper by a JSA paper from early 90s by so one of the guys called Casanova, the other is called Mateusz, can you recall it? Because I constantly forgot those names. And of course I didn't put them on slides because Casanova Ferreira, it's not Ferreira, it's Ferresh Mateusz, do you remember or not? Okay, I'll try to find the reference after the talk. So in the early 90s, there was a paper that investigated precisely this kind of...
Casanova's Ferre, sorry.
Ferre, okay. Precisely this kind of question of how you can, what can you save from omitting types if your theories are not complete. So here we had to build on their ideas, but not in a very direct way. But what we took from there was kind of an idea of contradiction analysis of those theories. Okay, so now this is the proof of the result. So if you have a theory which imposes recursive saturation in a countable language, then it defines UTB minus. Take such a theory, will inductively define a sequence of sets of formulae, those will be A alphas, and a sequence of theories U alpha. You take your language of your theory U, you add an extra constant A. You start with your theory U. At each step, A alphas are those psi's such that some phi defines the type tau. So those are possible conditions. This is the set of possible conditions which allows you to define the type tau. So define elementary diagram with some formula phi with parameters up to A, assuming that A satisfies this condition psi. So there are a set of possible conditions you can impose on the bound on the portion of elementary diagram you try to construct. I know how late it is, so but I mean I know I have 6 minutes or so. So I'm trying to wrap it up rather sooner than later. So recall once more what tau is. It means Y is a code of elementary diagram up to A. Of course, it makes sense to write tau type here. It's an infinite theory, and one infinite theory proves another. Now, you extend your theory in the following way. Take U alpha and say A does not satisfy any of those simple conditions for which you can define the portion of the elementary diagram up to A. So this says A is one of those hard cases. So in U alpha plus 1, all the simple reasons why tau should be definable in U alpha fail. Now we know more about A, so maybe there will be maybe we'll get new simple reasons, right? It's this contradiction part. So you kind of chop off a bit of possibilities, you restrict your space of possible types of A. And now dilemma. This process is actually non-trivial. It's not, it's not obvious from the definition. So I know it might be a bit obscure. Actually, you don't have to distinguish between formulae psi and phi for the sake of the proof. You can treat them very uniformly, but I think it's more readable if you write it that way. And you can actually, so that's something we're interested in. You can actually rephrase it as follows. If U alpha is consistent, then you have, you have A alpha is not contained in U alpha, which means you actually have such non-trivial conditions which would make it simple for A to define, for A to be one of those parameters for which you can define a portion of a truth predicate. So the claim is where you use something like omitting types theorem. You here use the fact that U alpha entails recursive saturation. And here is where you use countability of the language. And we don't know whether this is an important assumption. Okay, so let's go one slide back. So you start with U. At each step, you take those formulae such that if a formula holds of some element, then you can easily define a portion of the truth predicate for that for parameters up to that element. And now in the next theory, you say A is one of those hard cases. All those simple reasons why tau should be definable fail. And now you say that U alpha plus 1 is never the same theory. I mean, as long as U alpha is consistent, then U alpha plus 1 is not the same theory as U alpha. Of course, that way you get an infinite chain of increasing theories indexed by ordinals. So this has to stop. Notice that we still are simply using one and the same constant. We're not exploding with the constants. So at some point that gets inconsistent. It has to be a successor step because of the limit steps we simply take unions. Since it is inconsistent, there is a finite set of formulae at some step such that this set is inconsistent. In particular, U alpha proves that at some point after you chop off and chop off and chop off all, you say that no, A is very much harder than what you thought. No, A is very much harder than what you thought. At some point you have to stop. Okay, so A actually has to be easy. So it's one of those finitely many conditions of why it's easy to define elementary diagram for A. Now you take any model. I know how little time I have. You take its countably saturated elementary extension, so you saturate it. Take the least alpha such that one of those simple reasons holds cofinally. We claim that it exists. If it doesn't, then by saturation, each of those theory U alpha has to be satisfied, right? No psi alpha exists up to from some point on. There are only countably many such psi alphas at each level, at each of those steps. So from some point on, only the negations of psi holds. So this means that your model is actually divided into the regions in which bigger and bigger, like theories with bigger and bigger index holds. It actually is divided like this. And well, by contradiction, like reasoning the contrary, you would actually have, you would actually hit the last theory and you actually hit this finite collection of formulae, and one of them would hold above some bound. In particular, there is some formula that holds cofinally contrary to the assumptions. So now this is the reasoning by contradiction. I'm not saying that this last alpha we hit is from where psi comes from, but we know that this alpha exists. I know I almost so what we say in the, I know I should finish. So let me.
I think you could take like 10 more minutes or 15 more minutes if you need.
Oh, okay. Then I can safely take you to the shore. So I need 3 more minutes. So there is one of those reasons why it should be simple to define a truth predicate, such that it holds. Such that it holds. Let's call this guy. So it holds cofinally. It's in A gamma. Since gamma is the least such, what it means is that here in this region, actually, up from some point on, actually, it might be this region. Actually, here, all the previous A alphas, all the previous simple reasons fail. So starting from here, we're in the realm of U gamma. So this C has to actually be the simple reasons because this only works fine in U gamma. Take a formula that defines this type tau. By minimality and countable saturation, as I said, there is a bound such that above this bound you have all the simpler reasons fail for why elementary diagram should be definable. In particular, above this B, above this bound that they just marked with this very aggressive stroke. If C is satisfied, then actually any B, then actually any C, B is reserved for a bound. Any C that satisfies phi of AC actually satisfies tau of AC. So actually it does code the theory of the elementary diagram of the model up to A. Yes. So now you can define the tau star, T star, as we wanted to do this in our naive attempt. You take all the sentences such that for arbitrarily large A, for which psi of A holds, there exists a B for which phi of A B holds. So this B is now our portion of elementary diagram up to A, and phi is in B. And now this does satisfy UTB minus. Okay. This definition, if you like, I know it's not clear what from what I wrote here, from what I literally wrote, but if you unwind this definition, it actually does use parameter. So you cannot just say for an arbitrarily large here, you should say how large this A is supposed to be. So since when is psi supposed to actually define portions of a truth predicate? So it seems we didn't win much. It doesn't need to carry over to M. But at this point, I could either use Mateusz's remark that in particular, we know that if I can define UTB minus with predicates, with parameters, then I can intersect over all definable UTB minus predicates that I can define without parameters. So let's repackage this argument. Yeah, I think that what I said is literally not true, right? We know that I mean, what Mateusz said actually depends on the uniformity. So please ignore my last remark. Let's do this as in the slides. So this theorem, this definition uses parameter B up to this point, but we can get rid of it. So let's denote by formula T star B the formula defining it, but with B made explicitly a parameter. And now define T as those formulae, those sentences, such that their depth is less than some D, such that for all large enough B, now I quantify over B, T star B satisfies Ct minus up to D. So phi has small depth, so small that T star B actually satisfies compositional conditions up to that depth. And this sentence phi is deemed true by all such large enough, T star B's. Right. So now in M star this satisfies Ct minus up to some cut I. This can you show probably. In particular, I mean, in fact, so it has to satisfy Ct minus. The definition does not use any parameters, so it carries over to M without any changes. Whew, we're done. I know it was a bit fast, but the time is not also we're not very like rich in time here. I'm very sorry if it was too fast. So now a few remarks. So you could replace dependence on the model on the dependence with a completion of a theory. So if U is a complete theory in a countable language, which implies recursive saturation and defines a UTB minus predicate. The predicate satisfying UTB minus is defined in every model without parameters, just by the proof or by Mateusz's observation from the last talk. If U is not complete, then the dependence of the theory is not uniform, as we have seen in the previous example. And this formula cannot have bounded complexity. This again follows by Mateusz's remark. So everything here is very non-uniform typically. Right, this answers Albert's question. So this goes back to the previous counterexample. So in this predicate that satisfies UTB minus, doesn't have to be definable in U for a U that imposes recursive saturation and extends PA, even if we assume that the language is finite, that we don't know. I mean, as far as we know. I mean, we have a counterexample. I'm sorry, we have a counterexample. It doesn't have to be. This exactly addresses Albert's question. And what we don't know about this particular part of our research is whether in our counterexample, whether we use countability of the language. So we use something like omitting types. Do we have to? We don't know, but we don't have a counterexample either. Suppose that you have a finite theory, it extends arithmetic, some fragment of arithmetic, and it imposes recursive saturation. Does it define a UTB minus predicate? We don't know. And finally, we showed that if you impose recursive saturation, that you can define UTB minus. That's nice. But UTB minus actually has nothing to do with recursive saturation, right? It doesn't imply, it doesn't impose recursive saturation. So can you find a stronger theory here, stronger than UTB minus, which does impose recursive saturation, which you could also extract from this theorem, or from a theory that does impose recursive saturation? Okay, I'm very sorry for 8 minutes of your extra time. It was very nice to be here. I hope I didn't discourage you completely from the topic. Thank you.
Thank you very much. So let's all thank Bartek.
Bartek.
Again, that was perfect in terms of time. Are there any questions from the audience?
Well, I have one question, or maybe one and a half. But first of all, thank you, Bartek. I certainly was not discouraged at all. Thank you very much for the lecture. But when we have a list of those in remarks, the previous slide, can you go back? Right. So all those remarks, in particular the first one, a complete theory. But look, there is something about this result that I can call mine, is that would really be interesting to have something to say about theories that are that the standard model is expandable to. But that's of course a non-starter, because in the standard model everything is inductive. So my result would cover it. But but in the sense, for example, but in the standard model, this is the source for looking for interesting theories, where this is theories, and then you look for non-standard models of those theories. Theories come from some standard or less standard, but identified semantics. So in this first example, when you say U is a complete theory, what could be an example, a natural example of such a theory?
Okay, so of course now it depends on your question of what natural means, but the counterexample we've given. So this is model situation, like typical model. Okay, so I have two examples. So both counterexamples we've given. Okay, so the second counterexample I've given, I would say it's an example of such a theory
Right. But I know I see that. But in a sense, what's done in those theories, you code in the notion of recursive saturation.
Yeah.
But
I mean, not this counterexample, but the second one. So this one with, is it natural? I don't think so. But
no, it's not a question of criticism, but somehow that. But as I said, as opposed to, if you look at those complete theories that come, like the complete theory of the true satisfaction, for example, or complete theory of a generic subset, or a complete theory. So it sort of, it refers to something, well, natural may not be a good word, but something, in the sense, in this sort of study of non-standard models, they are non-standard models of some standard situations. And that's where the theories come from. That so in this sense, it would be interesting to have something that maybe violates induction to some extent, but still comes from some somewhat standard situation. Last time, and it's a pity that Ken is not here today. Ken always have this universal question: what about models of ZFC? Right? Is there something? Are there some natural examples that could come from there?
Yes. Okay. I think that's a very valid point. I don't have any particular simple answers now, since I think our motivation was a bit different. We're really coming from general study of theories. So our motivation was mainly to get a toolbox for distinguishing true theories. So as Mateusz said, our first question was, suppose you have a finite theory, it defines TB minus, does it define UTB minus? So suppose you have a finite theory which defines one truth predicate, doesn't define the other. So can you define Tarski biconditionals without doing it uniformly? And then we tried to introduce a number of properties that truth predicates can have, with the hope that we can show this separation by showing that getting a theory which has one of those properties and doesn't have another. So our motivation wasn't coming from a study of a very particular example. If I understand, okay, so that's first and honest answer to your question. A more not so honest, but like more literally answer to your question. So can I have an example of a theory that imposes recursive saturation?
Right. That says something interesting, something completely not connected to satisfaction, realization, truth, some theory of something.
So one thing I would say is, so we have this counterexample where you can have a theory. This theory, as we defined it, it did contain induction. So it said, well, take infinitely many truth predicates, and one of them will be truth predicate, but we don't know which, right? It is an artificial and contrived example in a way. It's an example of something. It's a counterexample to something, but it's a situation you can actually imagine. So now we know that in the presence of induction, it does have to satisfy UTB, and it's kind of actually obvious from this example. So like here you already written up your candidates, you named it, but now the theorem kind of was from the question of whether this is the only kind of counterexample you can essentially have. So one answer is that no, of course. I mean, in a trivial sense, you can of course prolong this sequence. So you can say, okay, but then T omega either satisfies itself or it doesn't, and you can go on with it. And then T omega plus 1, if it doesn't satisfy, then T omega plus omega will. And if T omega plus omega will not, blah, blah, and you continue that way. So we are kind of interested whether this is the only kind of possible counterexample, or are there more phenomena that can stand behind defining recursive saturation? And it turned out there cannot be. So actually you will always find, in a way, this kind of structure in a model in which recursive saturation, in a theory in which imposes recursive saturation. Of course, it doesn't address your question, but I think it's a very valid and good question. Oh, and
I think we lost him, but thank you for your answer, and he can catch up on the video later, I think, if he needs it. I have a question, but let me see if Albert or Mateusz or Laurie has one. So, anything from any of you? No? Okay, so just kind of a general question to, I guess, to both you and Mateusz, because I said this personally to Mateusz earlier, but what can you say anything about CT or CT minus in terms of basically the same kind of questions? Like, what is there anything that's known beyond? I mean, beyond Laughlin's theorem, essentially.
One stronger thing is that one I kind of hinted to before. So we have the strengthening that CT minus also defines UTB, so we can add induction. And there was a technique which we call disjunctions with static conditions, which kind of allows you to repeat the kind generalizes Laughlin-like constructions. So do we have any, I understand your question of, do we have any other further evidence of what else CT minus does? I think it's a perfect question. I mean, it's a question I spent personally a couple of years thinking of with no effect, and I would be very happy to return to. So in particular, I was trying to understand whether in every very simple question. So we have one nice and neat counterexample to property stronger than recursive saturation. So having satisfaction class. Truth-like property, of course, there are other notions of saturation. So suppose that you have a UTB class. Do you have CT minus? We don't know. Not at all. So we tried to play around with rather classless models of UTB to no effect. I mean, it's a question, and like take a theory, like conservative theory stronger than CT minus. Maybe if you can get a stronger theory, you show that not all of those of its models are models of UTB. We don't know. As for definability, it's Albert's result that actually CT minus that it does not define for UTB for some rather general, not quite so trivial. It's a very neat argument, but for some general proof theoretic reasons, it cannot define it. But as far as for model goes, as far as we know, it might be literally the same. So CT minus, for all that we know, models of CT minus might be the exact same things as models of UTB. So any stronger property that would reverse to CT minus would be very interesting to me. And personally, to me, and as I said, it's something that I'd very happy to get back to, but just any attempt thus far.
So just naively, does the question become easier or harder if you? I would suspect it would become easier if you just look at CT and throw in full induction into the language. You have fewer models to work with, right? But you have a stronger arithmetical theory, but sure, like let's just focus on that. Do you get? Is there anything that just jumps out that's obvious there, or no?
In a way, that's now becomes a bit incomparable because it's not conservative, right? So now you're not in the realm of analyzing what happens to models, and then you'd have to look for properties of the stronger arithmetical theory. But no, I don't think we've looked at any particular model theoretic properties of those, like any new model theoretic properties of those. No, I don't know of any. I mean, the region above UTB. I mean, the UTB is the strongest, like the strongest notion of saturation I personally know. Of course, there is resplendence above it, right? So UTB doesn't entail resplendence. It's inductive theory, right? So you can have rather classless models of UTB in the language of truth predicates. So it's not, of course, resplendence is above everything. But
go ahead, Mateusz.
Yeah, so I'd like just to add one thing to Bartek's great comment, that great answer, is that it seems that we do know one theory that also model theoretically defines UTB and seems to be incomparable with CT minus with respect to definability. There is this theory PT minus, in which you have partial conditions, so you don't have full commutativity with negation. And if you add to this theory a sentence that all induction axioms are true, all, more precisely perhaps internal induction would be better, then it defines UTB by Bartek's argument. But this partiality seems to make it incomparable to CT minus, and the other way around, CT minus is fully classical. So this partial, it seems likely that you cannot define CT minus, PT minus plus internal induction. But I think that basically we left these problems like 2 or 3 years ago, and since then we haven't looked at them. Because, I mean, they seemed hard.
Yeah, I'm still just that I still find it interesting. There's nothing wrong with those problems. I simply tried one attempt at it after another, and I ran out of ideas. So once I get back,
So I'll ask a slightly different variation of the same question, but essentially, and it's not the same question, but it's the same idea in my head. You have these, you've laid out these different parameters of what you want your theory U to do, right? It could impose elementarity, it could impose some other stronger conditions. If you go from elementary equivalence to elementary as a substructure, you get some improvement in strength. What if you then sort of make the language even richer, L omega 1 omega something like that, so L omega 1 omega equivalents, or different levels of increasing the logical strength of the assumption. I wonder, yeah.
Supernatural direction. I mean, but this whole subject is, I mean, it's something I don't have any, I mean, I think it's interesting, but like this whole reversal to model theoretic properties of truth is something we investigate for a year or so, like maybe slightly more than a year. And so there's many interesting things you can ask, which we haven't yet simply asked, right?
That's fine.
So I think it's a perfectly valid, good question, right? What?
All right, no, that's what. Laura, I think you had a.
I think I hear you.
I can't hear you. I'm sorry.
Can you hear me now?
Yes.
Yes.
Sorry. 2 short questions, I hope. What a naive question. What happens if you don't have, if you only have sigma 1 induction with the added predicate? No. But can you get anything from that?
Right. Okay, let me think for a moment. Okay, so maybe, but then it doesn't follow from any of the arguments. So Roman's argument used conservative extensions, which is equivalent to induction. Theory have those only if it has induction. So it doesn't follow. There is no uniform dependence in any of the theorems. So there is no like natural hope that there is uniform correspondence, and I doubt that there is uniform correspondence. So if the question is, if suppose I have sigma 1 induction, sigma n induction on one side, do I have sigma n induction for truth predicate? Then in general, the answer is no. So, I mean, you could cook up a counterexample to this. To a broader question, is there some other kind of property other kind of truth theoretic property I could hope for? I could, like milk from this theory if it happens to impose recursive saturation satisfy some induction? Then the answer is maybe. I mean, it's a very interesting question, but it's not, it's not a simple correspondence that we know.
Thank you. The other question, my memory is not clear, but in the 1980s, there's some work, I think, by Ratajczyk, and he characterized having a full induction class in terms of a Ramsey style property on the model. So I just thought maybe that kind of combinatorial analysis could help you to separate these theories.
That seems very relevant and very useful remark, and thank you for it, because I think I was completely unaware of this work and this result, and it sounds very, it sounds very useful and relevant to what we're doing. So I simply wasn't aware of the work, and thank you so much.
Yeah, I might be able to find it. I'll let you know.
And we all know, Laurie, maybe it could be posted somewhere. The answer, also the place where the paper is.
Yeah, okay, I'll have your email from the from this list. So yeah.
Okay, so let's wrap up and thank Bartek again. Again, that was very, very interesting. Thank both you and Mateusz for the two-part talk. This was really interesting. Next week we have Cezary Ciszynski. Again, apologies on the pronunciation. I got that one. Okay. All right. Thank you. And he will be talking about the principle of disjunctive correctness and some recent work that I believe all of you are probably familiar with on that. So really sounds interesting. I hope to see you guys there. And again, the recording of this will be available on YouTube in the next day or two.